Alright everybody, we're going to be talking about periodic motion today. Periodic motion, simple harmonic motion, period amplitude. So, what they are. Periodic motion is any motion that repeats. So over here, I've got a spring going up and down. And when it's all the way down at the bottom, it's right here. And when it's up at the top, it goes up to here. So this thing is oscillating between these two things right here. And how far it goes from the bottom to the side. So I'm looking at the bottom of the box the entire time. We call this the amplitude. And we usually measure it in meters. So amplitude is the distance of quote-unquote vibration. Now, in periodic motion, things go back and forth. Now, the period, what the period is the time of vibration. Just looking at this thing right here, it looks like it's 1001, 1000. So it looks like about, this one's roughly around 1.8 seconds, I don't know, 2 seconds. We measure it in seconds. Here we measure amplitude in meters. Now, simple harmonic motion, what that is, all simple harmonic motion is periodic, but not all periodic is simple harmonic. Simple harmonic means that the restoring force is proportional to the distance moved. Meaning that the farther this spring is stretched, the greater the force of the spring wanting to pull it back is. And that's true over here. The farther you pull the spring, the harder it wants to go back. The farther you pull the pendulum, the harder it wants to go back to its original rest state. So there, simple harmonic motion. Now, Hooke's law relates directly to simple harmonic motion. Hooke's law says this. It's F equals negative K X. Now I'm going to go over here to the next page and look at Hooke's law. This is an example of Hooke's law. Like so, F is a restoring force, and we measured in newtons. X is a distance, the distance stretched, and we measured in meters. And K was what's called the spring constant, and we measured in newtons per meter. Now the spring constant is how hard it is to stretch a spring. So if you wanted to if it took 10 pounds to stretch a spring 1 foot, that would be 10 pounds per foot. Or in the metric system, 10 newtons per meter, something like that. The reason that it's negative is that if you're pulling this down with gravity, the restoring force is always opposite. So if you were to compress a spring up into it, it would force against you, and that's why it's negative. It's always against what you're pulling at. Now here's actually an example using the spring constant, and before I want to do that, I want to talk about the potential energy. There's one more. The potential energy of a spring is, the equation is 1/2 mx squared. So 1/2 I'm very sorry, not 1/2 mx squared. I'm thinking kinetic energy. Kinetic energy for motion is 1/2 mv squared, but potential energy is 1/2 k x squared. It's 1/2 times the spring constant times how far you stretched it squared. And here's an example in your book. It's example problem number 1. It says, determine the spring constant. How much is the elastic potential? So part A, determining the spring constant. So 18 centimeters is how far we're stretching it, so 0.18. We're looking for the spring constant K. And then the force, 56 newtons. So the spring constant K, now it doesn't matter if it's positive or negative. The negative is just there to tell you the direction. But the spring constant is 310 newton meters. So you take 56 divided by 0.18 newtons per meter. Part B, what is the elastic potential energy? So 1/2 times 310, and we're stretching it 0.18 squared. So you run that through your calculator, and you get 5.0 joules. Now what this is saying right here, this is saying that it takes 310 newtons to stretch this thing 1 meter. If you wanted to stretch it 2 meters, it would take 620. So you can use this spring constant to find out, like, how far do you need to stretch, how far would it stretch if you put this weight on it? How much weight do you need to stretch it this far? This is kind of like if you were to graph it, it would be the slope. Now back here, a pendulum. Let's talk about, well, actually, before I talk about pendulums, I want to look at the bobbing of a quick pendulum right here. This is a series of pictures taken at equal time intervals, or a motion diagram, meaning, like, if I made a position versus time graph for this thing right here, what I've got, it's starting down here, it's at the 0 point right there, and then it's back to 0. So what I've got is, it's kind of sinusoidal. So actually what I think I'm going to do is start it right here. I'll start my timer right here. So this stuff comes over here. Now what I want to make, I'm going to make a velocity versus time graph. And my velocity, if you look at this, we think about, where is the velocity 0? Well, the velocity is going to be 0 when it stops at the very top and at the very beginning. So the velocity is 0 right here and right here. Where's the velocity of maximum? Well, the velocity is going to be a maximum right there on its way up, and right here on its way down. It's very much negative velocity here and very much a positive velocity, so you end up with something like this. And you might be recognizing these as sinusoids, like they are sinusoidal in nature. They're repetitive, repeating. And my last one, I'm going to make an acceleration versus time. And that's the point of this one, to show you right here, when the ball is right here, there's an equal force up and down. So if there is no net force, that means that the acceleration is 0. So right at this point right here, the acceleration is 0. And also over here, there's an upward force, a downward force, they balance. So the acceleration is 0. So my acceleration is 0 here and here. Now let's look at it right here. I've got a very much big up force, small down force. So there is acceleration up. It's positive, so it's going to be there. And then let's look at it right here. Big down force, a restoring force provided by the spring, and an up force, so that the acceleration is very negative. So if I were to make an acceleration versus time graph, this is the way it would look. Just for a spring bobbing up and down. Now let's talk about pendulums for a second. What a pendulum is just a ball swinging back and forth on a string. Now, the forces that are at work here, like, you've got, no matter where this ball is, you've got gravity pulling it down, and you've got the tension on the spring. Now remember, we always add vectors tip to tail. So the net force is this vector right here. That's why the ball wants to gravitate to the center. It wants to end up right there because of that net force. The same is true on the other side. You've got a force provided by tension, you've got gravity, add them tip to tail, and you end up with a net force pointing towards the center. So no matter where you are, there's always some restoring force that wants to go right in the middle. Now, when you're directly below it, you've got the up force of tension, the down force of gravity. You add them tip to tail, and it wants to stay put. So a pendulum is just a weight on a bob that goes back and forth, a swinging weight. The pendulum period is the exact same, is exactly what it sounds like. It's the time it takes for a pendulum to repeat itself. Now be careful. It's not the time it takes to just go over, it's the time it takes to go over and back. Now pendulums ascribe to what's called, there is a way to find the period of a pendulum, and it's this. The period of a pendulum is 2 pi times the square root of L over G. Now L, what L is the length, and what G is gravity. Length and gravity. You'll notice that nowhere does it talk about mass. Mass doesn't come up in here because it's not related. It doesn't bear any matter on how fast a pendulum takes. This letter T right here is time, also known as the period, in seconds. Pi is just pi like we've always had it. And here's an example problem. It says a pendulum that's got a length of 39.6 centimeters and a period of 1.22 seconds. What's the acceleration of gravity at this location? So, the square root of L over G. Our length is 0.369. Gravity is what we're looking for, and the period is 1.22 seconds. So using a little bit of algebra, so I take 1.22 divided by 2 pi, and then I square it. Oh man, this is a little bit complicated, so I may have to pull up my calculator to take this through step by step. So I'm going to take, first of all, 1.22 divided by 2 pi, and I get 0.194. And that's equal to the square root of 0.369 over G. So I'm going to now square both sides. So I'll square it, and I get 0.0377. 0.0377 equals 0.369 over G. And I'm going to multiply G over and then divide by 0.0377. So G is going to be equal to 0.369 divided by 0.0377. So I take 0.369 divided by my answer, and I get 9.79. And does that make sense? Sure, because we usually talk about gravity being 9.80, but that depends on a lot of stuff: where you are, what sort of things you're around, your elevation. It's crazy. So that makes sense. All right. So that kind of summarizes everything that is called periodic motion. Motion that repeats itself. So springs bobbing up and down, pulling on a spring, pendulum swinging back and forth. Now the last thing I wanted to touch on briefly is resonance. Resonance is when you push on something that's periodic at the right time. So my pendulum that's bobbing up and down here over at the right, if you push on it at just the right frequency, meaning if I were to, like right now, push down, push down, push down, you have to push at the right time and you can build amplitude. So we're going to say forces at the quote-unquote right time to build amplitude. And you've probably done this when you're a little kid swinging. If you kick your feet at the right time, you can build amplitude in a pendulum. Radios are based on this. Breaking wine glasses are based on resonance. Resonance is why we can, there's so many different things that resonance is a part of that we take advantage of in the field of physics. And we'll get to that in a little bit. So, thank you very much for watching.